Hello everyone. In this video, it's titled Classification of Singular Points. I'm going to be going over several examples of some second order linear differential equations in which we're asked to identify first off singular points, and then more specifically take those singular points and classify them as either a regular singular point or an irregular singular point. Alright, and the first thing I'm going to show you is a definition of what it means for, hopefully you know how to find singular points. If I'm assuming if you're watching this video, you know how to determine singular points, and I'm going to be doing that in this video as well. And now I'm going to show you the definition of, well, once you've identified a singular point, how can you determine if it's regular or irregular? Alright, so before I get into these examples, let me pull up a piece from an ebook here, a differential equations book that I'm reading through. So I'll read this out loud. Right? A singular point x sub 0 of a linear differential equation. Now this is a second order homogeneous linear differential equation. Please know that the definition, these definitions here could be extended pretty easily, pretty naturally to orders higher than 2, right? Third order, fourth order, but I'm only going to be focusing on today second order equations. So you have, some function of x times y, the second derivative, plus some other function of x times the first derivative, plus some other function of x times y equals 0. So a singular point is further classified as either regular or irregular. The classification again depends on functions p and q in standard form. So this is the standard form for a second order linear, where you have the lead coefficient is 1. So basically you just divide through by this a2 of x. Then you have this function p of x attached to y prime, q of x attached to y. Now remember, if x0 is a singular point, that means that p of x and q of x, right, at least, well, or q of x, at least one of those, is not analytic at x sub 0. That means that either p of x or q of x or both can't be expressed as a power series centered at x sub 0 with some non-negative radius of convergence. Right, that's what it meant to be a singular point. Alright, so if you have a singular point, you get in standard form here. A singular point x equals x sub 0 is said to be a regular singular point of the differential equation if the function little p of x equals x minus x sub 0 to the first times p of x, and at the same time little q, which equals x minus x sub 0 squared times q of x, are both analytic at x sub 0. Again, what it means to be analytic at x sub 0 means that these functions can be expressed as a power series centered at x sub 0 with some non-negative, or no, I'm sorry, some just not non-negative, but a positive radius of convergence, right? R being positive. And a singular point that is not regular is said to be an irregular singular point. So if either of these functions, little p and little q, are not analytic at x0, then x0 is said to be an irregular singular point. So again, the key is here to start off by getting the equation in the standard form for a second order linear. And like I said, these definitions could be very easily extended to order 3 or higher. Alright, so having that definition down, let's go to our examples. I think I have 5 of them. I might not get to all 5. We'll see how long it takes to get through the first few of them. So my instructions for every single one of these, all my examples in this video, are determine the singular points. So first off, of the given differential equation. Then we're going to classify each singular point as regular or irregular. Alright, so this first equation, again, they're all going to be second order linear homogeneous equations. So I have x cubed times y double prime plus 4x squared times y prime plus 3y equals 0. This is not in that standard form. And I'll recap it here. What is the standard form? That's this: y double prime plus 1y double prime plus some function of x. I'll call capital P, like in the textbook that I just showed you, times y prime plus another function q of x, capital Q of x times y equals 0. This is the standard form. So I'll divide through by x cubed and simplify. And we'll say p of x and q of x if we're talking rational functions, like we're going to see in all my examples here today. P of x and q of x will be just I'm just going to be dealing with polynomials divided by polynomials. Right? So we'll simplify these and put them in lowest terms. So when I put this in standard form, that's just dividing through by x cubed and simplifying. We have y double prime plus 4x squared divided by x cubed, 4 over x times y prime, plus, and then 3 over x cubed times y equals 0. And obviously you can only do this for when x is a non-zero number. So x equals 0 wouldn't belong to, if we're finding series solutions, which I'm not finding solutions to this, I'm just identifying singular points. But if we were to find any series solutions to this differential equation, the interval of convergence wouldn't have x equals 0 in it. Alright, so I'm in this standard form. Now the p of x from the form is this coefficient here of y prime, that's 4 over x. And the q of x is this coefficient of y, which is 3 over x cubed. Now I'll tell you right now, and it's probably pretty easy to determine. Again, I'm not going to go into this. I'm assuming you know some things about power series. I'm not going to make this a power series video. But I'm hoping it's obvious to you, and you can tell that these are not analytic. Neither one of these. Not analytic at x equals 0. Right? Because one, they're not defined at x equals 0. Now that's not the only. That's not a condition. That's not a necessary condition, or a sufficient condition. Sorry. You can have situations where a function is not defined at a value, but it's still analytic there. Like, for example, the sine of x divided by x. You can express that function as a power series centered at 0 with a positive radius of convergence. So, like, just because they're not defined at 0 doesn't mean they're not analytic. But when you're dealing with rational functions, polynomials over polynomials, I'll tell you, that's going to be enough. Hey, this isn't defined at 0, so its derivative, none of its derivatives will be defined at 0. So you wouldn't be able to express either of these functions as a power series centered at 0 with a positive radius of convergence. And because of this, right, since at least one of these, right, at least one of these p of x, q of x are not analytic at 0, then and that's the only one. That's the only place that these are not analytic at. They'd be analytic everywhere else. The only singular points for this differential equation would just be x equals 0. Okay, so that's the first part of my instructions. Identify the singular points. So just x equals 0. And now we're going to see if is x equals 0 a regular singular point or an irregular singular point? So now comes that question, right? Is it regular or irregular? All right, so what I'm going to do is, like in the page from that text I showed you, form these two functions. Look at little p of x, which would be x minus x sub 0, or x minus 0, just x times capital P of x. Well, that would just be 4 when reduced. Now this is a simple polynomial. Polynomial functions are analytic everywhere. So this is analytic at x equals 0. So far so good. But not only does this function need to be analytic at 0 for it to be a regular singular point, but also this other little q of x, which would be x minus x0 squared, or x minus 0 squared, x squared times q of x. Well, x squared times q of x would be 3 over x when reduced. This is a problem. This is a rational function, not defined at 0, therefore you're not going to be able to write this as a power series centered at 0 with a positive radius of convergence. This is not analytic at x equals 0. And if one of these fails to be analytic at that value, then that singular point is irregular. All right, both of these functions have to be analytic in order for that singular point to be regular. All right. So since one of them fails, x equals 0 by definition, by the definition I showed you on that page from that textbook, is an irregular singular point. All right. So again, pretty straightforward, just following the definition. And that's all the rest of the examples are going to be like. Now, like I said, my examples in this video, I'm going to be dealing with just polynomials and rational functions. But just know that you may come across, like I said earlier, like the sine of x divided by x, and you might think, oh, that's not defined at x equals 0, but it is analytic there. All right, because you can express something like that as a power series centered at 0 with a positive radius of convergence. So just be careful if you have functions other than polynomial showing up. But I'm going to do some simpler examples in this video, and maybe I'll get to a video where I do other kinds of coefficients, other than polynomials later, but for right now we're just sticking with polynomials. Okay, so next example, same instructions. So again, this is another second degree. They're all going to be second order linear homogeneous differential equations. This one again does not start in standard form. Now x squared minus 9, that lead coefficient, that factors to x minus 3 times x plus 3. So I'm going to divide through by that, and we'll also simplify the coefficients. So I get this into the standard form first so that we can identify our singular points. So we have y double prime plus, and then x plus 3 divided by this would just be 1 over x minus 3 times y prime plus, and then 2 over this, right? 2 over x minus 3 times x plus 3 times y equals 0. All right, so now I'm in the standard form. That capital P of x is the coefficient of y prime here, 1 over x minus 3. That capital Q of x is this coefficient here, 2 over the x minus 3 times x plus 3. And again, I'm only dealing with rational functions. So rational functions are analytic everywhere except at wherever they're undefined. All right. So this p of x, this is analytic at all x except x equals 3. Right. And this q of x is analytic at all x except 3 and negative 3. Oops, sorry, analytic at all x except x equals plus or minus 3. Right. So recall the definitions of ordinary point, singular point. If either one of these functions is not analytic somewhere, then that particular value is a singular point. So 3 and negative 3 are the singular points of this differential equation. Right, so the singular points are x equals 3, x equals negative 3. All right, so again, that's part 1. All right, just identifying the singular points where this p of x and q of x are not analytic. And then taking these one at a time, I'm going to determine, take x equals 3, say, is it a regular or irregular singular point? And then do the same with x equals negative 3. Right, so now I'm going to ask the question, regular or irregular. All right, so first, x equals 3. So again, I'm going to form that little p and little q that were mentioned in the definition. So little p of x would be, x minus 3, it's not 0 this time, to the first times capital P of x. Well, if I do x minus 3 times capital P and do some simplifying, that would just be 1. And that is clearly, it ends up being just a straight up polynomial, which is analytic everywhere. So it's definitely analytic at x equals 3. So far, so good. So far, it's looking like it might be regular. But then don't forget, I also need this little q of x, which would be x minus 3 squared times p of x, or sorry, capital Q of x. I need this to be analytic at 3 as well. Well, if I multiply x minus 3 squared times q, right, times this q here, the x minus 3 in the denominator would go away. I'd have 2 times the quantity x minus 3 in the numerator divided by x plus 3 in the denominator. This is also analytic at x equals 3 because now it's a rational function that is defined at x equals 3, right? I don't have x minus 3 in the denominator anymore. And since both of these are analytic at x equals 3, then x equals 3 is a regular singular point. Wonderful. But now I'm going to check, x equals negative 3. So again, I'll form that little p and little q, right? So little p of x would be, x plus 3 times capital P. Well, that would be x plus 3 divided by x minus 3. And this is defined at negative 3, rational function defined at negative 3. So it would be analytic at x equals negative 3. You don't have x plus 3 in the denominator. So far, so good. Looking like x equals negative 3 may be a regular singular point, but it does have to satisfy both. It has to, both of the functions, little p and little q, have to be analytic at x equals -3. So q of x being x plus 3 squared times capital Q, well, that would cancel one of the x plus 3's in the denominator here. I'd have 2 times x, the quantity x plus 3, divided by, and then x minus 3 still, and that would also still be analytic at x equals -3, right? You don't have an x plus 3 in the denominator anymore. It's a rational function, and rational functions are analytic wherever they're defined. So wonderful. So since both of those are analytic at x equals -3, x equals -3 is a regular singular point. Fantastic. All right, so I'm going to move on now to a third example. I guess before I do that too, just pay attention to how things could be easily affected by powers. Like if for some reason this was x squared minus 9, squared, and these two are both squared or raised to higher powers than 1, well then you can check this for yourself. X equals 3 would be an irregular singular point. -3, I think, would still be a regular singular point, but I would leave that to you. Just know that powers and whatnot will definitely have an effect on what singular points are regular and irregular. All right, so let's look at another one. So again, all polynomial coefficients here, not in standard form. So I'm going to get in that standard form with the lead coefficient of 1 and simplify the other coefficients. Now x cubed plus 4x is, when you factor it, is x times x squared plus 4. So if I divide through by this, we have y double prime minus, and then the x would cancel. You have 2 over x squared plus 4 times y prime plus, and then 6 over x times x squared plus 4 times y. Alright, so the p of x and q of x, the capital P and capital Q. P of x is -2 over x squared plus 4. The capital Q equals 6 over x times x squared plus 4. And we're actually going to be looking at the entire complex plane for ordinary points and singular points. So imaginaries will be involved as well sometimes, like in this case. So the only places the only values of x for which these functions are not defined, and being rational, if they're not defined, they're therefore not analytic. We get our singular points at those points, right? So the only place where these aren't defined are 2i and -2i, right? Imaginary would make the x squared plus 4 equals 0, and x equals 0, right? Would make this denominator here 0. Right? All right. So really, if you want, you could break up x squared plus 4 into x minus 2i times x plus 2i, right? And in fact, I'm going to think about x squared plus 4 that way, because it'll help me when I go to talk about, are these singular points regular or irregular? All right, so x equals 2i. Well, let's start with x equals 0. So I'm going to form that little p and little q. All right, little p would just be x to the first times capital P, which is -2x over x squared plus 4, or x minus 2i times x plus 2i. And then the little q, x squared times capital Q, would be 6x over x squared plus 4. And both of these are defined at x equals 0, and being rational functions, they therefore be analytic at x equals 0. So this tells me that x equals 0 is a regular singular point. Alright, so that's x equals 0. Then x equals 2i. And form little p, little q. Now little p would be the quantity x minus 2i times capital P. Which again, if you think of x squared plus 4 as x minus 2i times x plus 2i, that'll make this a little easier. This will be negative 2 over x plus 2i, which would be defined at 2i. And then q of x, little q, be x minus 2i squared times capital Q, which will be 6 times the quantity x minus 2i divided by x times x plus 2i, which is defined at 2i. So both are analytic at x equals 2i. So yet again, we have another regular singular point. So x equals 2i is another regular singular point. Similarly for x equals negative 2i. Because again, x plus 2i is only to the first power down here, first power down there. If it was like to the third power, like in that first example, we have an irregular. So I'll just leave this one to you with the 2i. So similarly, x equals negative 2i is a regular singular point. So far, we've had a lot of regular singular points, and I think just the one irregular from the first example. But it's really just a matter of doing these simple checks, right? So I got 2 more. I'll do all 5. Why not? Because the more you see them, the faster you get at them, especially when you're dealing with just polynomials as exponents like I am here. So x squared plus x minus 6, that's x plus 3 times x minus 2. Divide through, we get y double prime plus then 1 over x minus 2 times y prime plus 1 over x plus 3 times y equals 0. So I'm hoping you can see now that the regular points are x equals 2 and negative 3. I'm sorry, not the regular points, the singular points. Did it again. The singular points of this equation are x equals 2 and x equals negative 3. And for x equals 2, basically, I got x minus 2 to the first here, and, x minus 2 to the 0 here. As long as its power is 1 or less in the p of x denominator, and its power is 2 or less in the q of x denominator, it's going to be a regular singular point. So x equals 2 is regular, and the same for x equals negative 3, because again, you'll be dealing with x plus 3, and the power of x plus 3 is 0 in this first denominator, so it's 1 or less. And the power of x plus 3 is 1, meaning that it's 2 or less in the second denominator, the q of x denominator. So again, when you go to check, both of these will be regular again. Right? So far, lots of regular singular points and just the one irregular in the first example. But now finally, I promise you, this last example has a mixture. Has a mixture of irregular and regular. Alright, so here, this polynomial, this is x cubed times, x minus 5 times x plus 5, right? That's x squared minus 25, and then times x minus 2 squared. And if I divide through by everything, put it in standard form, we'd have y double prime plus 3 over, let's see, one of the x's would cancel, so I have x squared, one of the x2's minus 2's would cancel, I have x minus 5, x plus 5, x minus 2. Alright, so there's the p of x, the capital P. And then here, just the x minus 5's would cancel, so plus 7 over x cubed times x minus 5 times x minus 2 squared, times y equals 0. And there's the q of x, that capital Q of x coefficient. So the singular points, I hope again it's obvious, are where these rational functions aren't defined, right? They're therefore not analytic. So the singular points are x equals 0, x equals 5, x equals negative 5, and x equals 2. Now we check, are they regular or irregular? Now x equals 0. I'd be multiplying this by x and this by x squared. Well, if I multiply this by x, there's still an x in the denominator, so it's still not defined at 0, therefore not analytic. So this is irregular. X equals 0 is an irregular singular point. Now x equals 5, how about that? I'd be multiplying by x minus 5. Now if I do that to here, and then I'll be multiplying this by x minus 5 and this by x minus 5 squared. And either way, there'd be no factor of x minus 5 in the denominator anymore. So the resulting function would be, defined at x equals 5, and being rational would therefore be analytic at x equals 5. So x equals 5 is regular when I'm asking about x equals negative 5. I'd multiply this function by x plus 5 and this one by x plus 5 squared. That would cancel the x plus 5 here, and so in either one there'd be no more x plus 5 in the denominator, so again I have a regular singular point. And then for x equals 2, I'd be multiplying by this by x minus 2 and this by x minus 2 squared. When I multiply this by x minus 2, the x minus 2 in the denominator is gone. When I multiply this by x minus 2 squared, the x minus 2 is gone in the denominator as well. So again, I'd have two functions that are analytic at x equals 2, regular. So 3 regular singular points at 2, 5, negative 5, and 1 irregular singular point at x equals 0. So again, you can see how, the first and second example I went pretty slowly. Use the definition. I still use the definition for the other 3 examples. I just thought about them, said them out loud. Because, you should, especially with polynomial coefficients like this, you should be able to do these pretty quickly with some practice, like I just did this last one. And that's it. So hopefully watching me do these, go over these 5 examples of second order linear equations with polynomial coefficients, hopefully you can identify singular points and whether or not those singular points are regular or irregular using that definition. And thank you very much for watching.